Day of Physics 2211, and this is my lab report for Lab 5, the rope swing. For this lab, I chose to analyze the world's largest rope swing. Specifically, I wanted to analyze the motion of the jumper on the rope, collect data, and use this data to create a predictive model of the motion using GlowScript. Using this model and data, we will be analyzing the energy of the system, determining the effects of drag on the system, and finding the maximum velocity of the rider. Some of the concepts that we will be analyzing are spring force and oscillation, kinetic energy, potential energy, weight and drag force, and Newton's second law. So to go in more depth, first we have the work energy principle, which is that this is a closed system, so the change in energy is zero and is equal to the summation of the potential energy, the gravitational energy, and the spring energy. The spring potential energy is due to the position of the spring and is 1/2 k times x squared, where k is an arbitrary constant. The gravitational potential energy is energy due to Earth's gravity, the gravitational field that is, and is equal to the mass times 9.8 meters per second squared times height. Lastly, the kinetic energy is the energy of movement and is equal to 1/2 the mass times the velocity squared. On the other side, from understanding Newton's second law, we are able to understand more about the kinetics of everyday motion. The law states that the rate of change of momentum is directly proportional to the sum of all forces acting on the object, which then can be related to velocity, as the change in velocity is equal to the net force divided by mass times the change in time. The sum of force statement is all of the forces acting on a system. The net force is equal to the gravitational force plus the spring force, and once we include drag force, it will also be plus the drag force. Hooke's law models the motion of a spring where the force is equal to the negative product of the spring constant, which once again is an arbitrary value. It is determined by the material and size of the spring multiplied by the displacement from the relaxed length. Lastly, the drag force is a force that opposes motion. It basically accounts for all resistive forces and is calculated by using a factor b, which is experimentally determined, times the velocity squared. Unfortunately, the video of the motion of the rope swing is not good enough to analyze using Tracker, but we are able to collect the following initial conditions from the behind-the-scenes video. The mass of the rider can be assumed to be 70 kilograms because that is the average mass of a person. The length of free fall is 39.6 meters, the rope length 45.72 meters, the distance from the ground is 3.05 meters, the total time of the ride is 20 seconds, and the spring constant can be determined to be about 10,000 newtons per meter from a sum of force statements or by Googling the average spring constant or strength of climbing rope. From this information, we create the GlowScript model. On the left side is basically just updating and defining. Line 47 is the person's mass, 50 the initial position, 67 the spring constant, 70 the length of the rope, 72 to 74 the vectors that define the spring force, and 77 through 80 defining the energies of the system. On the other side, in lines 92 through 95, we define the initial energies. 98 calculates the gravitational force, 101 calculates the spring force, 104 the net force, 108 the velocity of the object, 110 the position, and 121 through 128 updates the energies and calculates the change in energy. This slide shows the result of the modeled motion of the rope swing and the change in energy / position graphs. The blue is the change in KE, red the change in PE, yellow the overall change, and green the change in spring potential energy. As we can see, the overall change in energy is 0 because the yellow line is flat, and as KE increases, PE decreases, and the reverse is also true. In order to figure out how drag affects the system, we need to include it in the code. To do this, we estimate the value of B to be about 0.4, calculate the force of drag using negative BV squared, and then include this value in the net force calculation. This slide shows the result of the modeled motion of the rope spring and the change in energy / position graphs. The blue is the change in KE, red the change in PE, yellow the overall change, and green the change in spring potential energy. You see that the graphs look significantly different than what they looked like when the drag force was not accounted for. The main difference is the graph is no longer symmetric and the change in overall energy is not 0. So what does this mean for energy conservation? In the model where drag is not considered, it is considered to be an ideal system. We saw that as PE increased, KE decreased, and the reverse is also true. At the maximum height, the potential energy was a max and kinetic energy was a minimum. At the lowest point, the opposite is true. The overall energy change was zero, meaning that the conservation of energy statement is true. However, this is not the same for when drag was modeled. Energy was not conserved in this situation. There's multiple times when the change in energy is not zero due to the fact that the energy is lost to the system because of drag. This is not the only effect that drag has on the system. Drag also caused the object to slow down over time and the period to decrease due to the fact that the object did not reach the same heights as previously. Assuming an initial velocity of zero, we can calculate the maximum velocity that the rider experiences. Maximum velocity theoretically should occur at the bottom where all potential energy is zero and the kinetic energy is at a maximum. From the graph, we see this is 400 joules, so we set that equal to the kinetic energy, which is 1/2 mv squared, and solve for v to get 3.38 meters per second. If drag was not considered, the speed would be significantly greater.